And I would say this with the parts is pretty cool because then you can also see the reaction forces at the joint locations, and that's for me that's a game changer to have this opportunity to really inspect a part, and this quickly, right? With all things I would like to have, right? So this is pretty awesome. Hey guys, welcome to another round of analyzing a truss system with joints in Inspire. So I got this model from Ahmed, thanks again for that, and we will be happily going into it and see what we can learn from it. So the focus will be on reaction forces and not too much to check them, but how to access them, and also just normal modeling of those systems. So we will cover the full range from importing the CAD file to our reaction forces. And yeah, then I will show you what's possible in Inspire. So let's get started. Now, let me just quickly jump over here. Sorry. Now, you see here, the truss system looks something like this, and this is a little bit more complex, like the last one we did. And you can see now the geometric properties. You can see there's a force of 800 newtons. This should be 600 millimeters, sort of about the image quality. But you can see it. And you can also now try to make up your mind about the equations governing this system to calculate joints and so. I will not do that here in this lesson or this video, but I will encourage you to do it on your own. And if you want to get a little bit of help here and there, that's absolutely no problem. Just shoot me a message or tag me in the comments, and I will also happily do another video of just getting the system, the equations for it, and calculating that by hand. But now let's focus on the process of how you would do that in Inspire. So let me quickly start from fresh here and import a CAD, because there's a message which you might find from time to time. So you see here, parts in your model contain geometry errors. So it's always a good thing to check that, but let's go into the repair. So you can see now here's a set of settings to your repair options. There's tolerances and stuff like that. Normally I will just go with the defaults and check then that geometry by hand. So the first thing you can check here is, because we are doing a 3D model, you can also see and see what we don't need. For example, if we just made up our minds, we don't want to simplify the model too much, but just use the very fast joint mechanisms in Inspire, then it would be a good idea to just get rid of all components which are not necessary. So let's go through them quickly. Now you see, for example, points and lines, you can get rid of those. You see it also highlighting in the model if you want to see where it is, but let's just go ahead and just delete the points and lines because we don't really need them. Oops, Control Z to save the day. Here again, I think this can go. Okay, now do we miss anything? I don't think so. That's okay. By the way, if you are happening to see some kind of shadows or so in the model, which may don't seem right to you, this is because I removed it, and that's the ground shadows. And as you can see, those are not really where they should be, but just that you know there's a preference for that, and you can simply deactivate it. Now, we have the model here. All geometry is set. And one thing I really like to do to just see or just track the model process is to use the motion tool. I know it's not the tool which is maybe the one you will use in the end for analyzing your structure, but it really helps to get an understanding of your constraints, your joints, and so on. So let's do that. Let's go into the motion tab and see what we can find here. So you can see here that there's this analyze motion button, and although we didn't really model too much yet, we just hit the play button. Just analyze the motion. That means it will analyze this model as it is, and what would you think what might happen now, right? I didn't define anything, there's nothing here, and we will play this game multiple times in this video. So let's see what happens, right? I click play, and I can also see, already see that the model is just flying above or upwards. Now, also the motion analysis takes quite long, and I know that there will not be a really complicated long motion, so I can go into the motion analysis settings and change the runtime from 10 seconds to 1, right? So that makes more sense. So run it again. Okay. Now, what do we observe? So it flies upwards. Why did it fly in the first place? Now, there is a force which is a little bit hidden, but you see gravity here, and that's also hinted with the shadows of the floor in the preference, right? So the floor was at the top of the model. That's just coordinate system things, right? So you have set, and set is pointing downwards in this model, and so it flew upwards. Now to change that, you see the force is gravity, and you can just simply press set again to invert the direction. And if I just run it again, you probably guessed it, it flies downwards. But we don't want this model to fly, so we have to fix it, and that's the first thing you want to do. By the way, I'm not sure if it's working or if it's... So this is something I do now on the fly. If it's working if I constrain the model in structural. But for motion things, you usually do the following. You go to ground and just select a part which is the ground, right? So this part will be the ground. This is fixed now in place, and yeah, so not much changed, right? So you cannot really identify it like this. You would see it here as a ground part 1, but you can always go into this little box icon at the top. So here, then you can see that there is in fact a ground part, right? Okay, so ground part is set. Now let's just play again. And now, what would you think might happen? All right, ground stays in place, all the other parts fly away. That's somehow expected, right? I would say that's expected behavior. Now, why is this thing flying away? Yeah, gravity, sure, but it's missing something. It's missing all the joints which are not modeled. You see that the hydraulic cylinders are modeled and not simplified by simple rigids or simple 1D structures. Those are really modeled in 3D. And so let's add the joints, right? So we can do that because we have the geometry. Okay, let's go to joints. And here you have the option to just find joints. So for example, you could say whatever values here and then find them, and we will do that in a minute. But if you want to be really sure that you're setting the correct values, you can go to the measuring option and just measure what's your typical cylinder diameter. So that's around 20 millimeters, and that's all valid for those cylinders, for the bores. Okay, so yeah, let's set that. Okay, so here options, and then for example 30. That should find all, and press on find. And you see, those are marked now, but those are not created yet. You can create them individually by just seeing here with the check mark, and if I click now, it will get created, and you can choose from different options like pin. A grounded pin would be a pin fixed in place, sliding pin, grounded sliding pin, bolt and socket. We will go with the default values. So you could do that by hand, or just simply press on the play or the check mark sign, and you will create all at once. And you see that also those joints are nicely put into the model browser. So for later review, you can always go back here and just see, look at the properties and stuff like that, right? Okay. Now, again, I created something. Let's hit the play button. What would you think might occur now? So we have put in joints. Think about, will it stay in place or not? Let's see. Okay, that was too fast. Let's go let's go a little bit slower. So you see, the joints are doing its thing, right? So joints are working, but somehow those hydraulic cylinders are not really working. Those are flying apart. And this is expected behavior because we don't have any contacts, and those are separate parts, as you can see. Just by sliding or hovering over the part, you can see this part is one part, and then this is another part. So those are not connected. Now in motion, you have a way of connecting those things with rigid groups. So that means those two parts, or all the parts in a rigid group, those are just staying together. So they are rigid, a rigid connection. So let's do that. Let's create a rigid connection, and it automatically selected the part. Now let's select the other one too and hit on create. And the same goes for here and here, and click on create. Right click and swipe to the left. So you see now in the rigid groups that you have defined two of them, right? Two rigid groups, and you could check them again and see if that's what you wanted, or delete them, make them new if you misclicked. Now again, let's see what's happening. Is it now fixed finally? It seems that way, right? Now, if a motion is done, right, it's not really showing too much, but if you're in that view that this icon is marked, then you can always click on the joints and see forces. So this will come in really handy if you do like a reaction force check and see if that is the same thing. But be aware, sometimes I observe that those values are not really those which I would expect from a hand calculation. So be a little bit aware. We might find this later on in the video. Good. Now we have that. So I would say from constraint wise, this is now all right. We don't have a force yet, but we can do for sure that. And the force also is respected here. So for example, if we go here again and see at the joint forces, you see that's X, Y, Z and the magnitude. And the magnitude is now 100 newtons. Now the question might be asked, why is it 100 newtons? Well, the only force right now is acting here is gravity. And so you would have to calculate the mass and do those kind of things. But you also could do a run without gravity, right? You could just simply go here and say gravity no and run it. And now the forces technically should be 0. Did it run? I think so, yeah. And you also can see by looking at that the forces are stabilizing. Not here because it's 0 and then it's just giving you numeric instabilities. But for the other one, you saw it went to a certain value and then it stayed there. That means this is not really a motion, right? It's just converging to a final state or steady state where you have no movement anymore and no force change. Just to keep that in mind. All right, so we have that. Now I would say joints are set and you have a good understanding of the model. Now let's switch sides and analyze the part. Because, well, before that, just let's put in the structure, the force here. Like that, 800 newtons, and the direction should be downwards. Okay. And if I hit the motion again, sorry for the confusion, but I wanted to have this as a starting point, to have the run without gravity, but with the 800 Newton, and just look at the forces, at the joint forces. So you can see now the magnitude is somewhat about 1275. And yeah, from a hand calculation perspective, this seems a bit strange. Because if you do a free body diagram and you have here the force with 800 Newton and the lever arms, well, I let you get to it, but just keep in mind, we now saw that with 1K, and here is also somewhat around 2K. And yeah, so this is a joint force here. We will do the reaction force check in the structural, and you will see that it's kind of different, and you can be a little bit more, yeah, just reaction force check to it in structural. That leaves a little bit less of a problem area for you. Okay, so you have that motion, you have understood the structure, it's working. Now, let's go over to structure. And now you would say maybe that the constraints, well, they are all set and you could just hit run. And what would you think would happen if I just hit run? Will it give an error, or would you think that this is just working fine? Let's try it out. Let's do the same thing, no gravity. We have a load case. Yeah, let's run it. All right, no support in load case. So ground and constraints, structural constraint, they are not the same thing. Ground is only valid for the motion tab, but the structural constraint view isn't. If you go to see here the loads selector, you can see that there is a force, but there's no constraint. Okay, so let's make one. Let's make a constraint down here. Let's fix it in all three coordinate directions and be done with it. And let's also check, that was the thing earlier, if I remove the ground now here, if the motion still works, because now it has a constraint, and it seems it does. So if you have a constraint already, you don't have to define the ground again. It can be even an error code or a warning that you have duplicate constraints and stuff like that, just as a hint. All right, so we have a structure, now we have a constraint. Does it work? Let's see. Analyze, run. Okay, it failed. Why did it fail? Your model is improperly loaded or supported. Now, what could be the cause for that? If you saw that ground is not really an option for the structure, then what might also not be a valid option for the structure tab from motion? What did we define? We did define the ground, the joints. Well, the joints also appear in the structure, so I think those are not a problem. But what else? Rigid groups. The rigid groups are not working because those are also just defined for the motion tab. So in structure, you would have to define them differently. And one very easy way is to just couple them to strictly together with a connector. So you go onto the connector, choose one side here, one side there, and don't flexible, just put it rigid. So you're really safe. And do that one more time, once here, and also rigid. By the way, if you right click and swipe to the left, you're still active in this connector. So if you click again on another connector, you see that you're still active here, and whatever you click now will affect this connector. So be sure that after you have done or created a connector, click somewhere else to deselect this connector and be ready to create another one. Okay, we have two connectors now. Will it work? Let's find out. So again, stiffness, no gravity, load case 1, run. And by the way, I'm using the SimSolid solver here. So SimSolid solver, you can very easily go to the reaction forces. If I'm there, you have the reaction forces, and now you can check, and this is a model sanity check I would really always do, to check your forces which are applying on your model are resembled here in the bottom and on your constraints. You see, force 800, reaction force 800, and really this is such a good thing here. You can really look into it, right? If you have just a magnitude, you might be a little bit wondering what is X and Y doing, so you can switch it over to components, and whatever you want as a reaction, you can get it here. So this is a pretty cool thing. All right, but as you might have noticed, it's not so easy to get the reactions from the joints. So there's no way of clicking here and getting the reaction force for the joint. The only way I saw was to go on parts and then select the parts. And now you see you're here, and then if you select one particular location, you can see now here that it has roughly 2000 Newton, right? Those two have each 2000 Newton in Z direction, so pointing upwards or downwards. And you see that's pretty interesting. That is this is completely opposite to the one we have with the motion, right? So if the motion result, so just keep in mind here was 4000, and here we have the over constraint. That's because of the rigid groups. But let's just continue. So I don't think those will impact the model. And you see here we have now, now it has 2000 newtons. Interesting. But it should have 4,000 newtons. So, you know, I think I have to go a little bit deeper into this one. I'm not really sure what it is showing here, but maybe it's the sum of all or so. That could be something, but that's really not what I'm completely sure of. But just note that it is different to the one you would get or expect from your hand calculation. So for example, here you have the 1200. Yeah, 1200 or 1.2k Newton. And if I go over to the structure tab and see here, I go to the reaction forces, to this part, and here we have 3,200. Yeah, so this one is the only one. So there's not two like here. There's just one 3,200, and that's also what I found out for the static calculation. So maybe somebody of you knows the answer to this puzzle. So I would be gladly to hear from you. What's the reason why it's in motion? Why it's so different? But this is expected, and I would say this with the parts is pretty cool because then you can also see the reaction forces at the joint locations, and that's for me that's a game changer to have this opportunity to really inspect a part, and this quickly, right? With all things I would like to have, right? So this is pretty awesome. All right, while not really covering the full potential of the motion tab, I would really strongly recommend, if you want to understand a system, try with motion. Try to setting up your joints and click on run multiple times. I mean, it doesn't cost much compute, you see. It's really easy on the compute side of things. So you can really step by step understand your model. And if you understand the model, you're quite more confident in the results. So always do that. Apart from that, I would also encourage you to do the hand calculation. So yeah, just go into it. You saw the screen at the beginning, and if there's any questions, I might do a video about the hand calculations later on. And yeah, just go with that. Thanks for watching, everybody, and have a great day, and see you soon.